This program is about pumps, specifically centrifugal pumps, and their use in oil and gas operations. When you're pumping air, oil, water, or NGLs, all pumps operate on one common principle. They move something from one place to another. A lot of different types of pumps are used in the petroleum industry. Two kinds are seen most often. Those with pistons or gears, they're called positive displacement pumps. And those we'll talk about today, centrifugal pumps. Another module focuses on positive displacement pumps, so we won't spend any time on those right now. So, when are centrifugal pumps used? Usually when you have to move a lot of fluid, like emptying storage tanks, moving processed fluids in gas plants, providing emergency fire water, circulating cooling tower water, and, well, many, many other applications. What we're saying is that you'll see and work with centrifugal pumps just about every day. So you need to understand them, and this module will help you do just that.
This is the first section of a 4-section module on centrifugal pump principles. This section introduces the various parts and operations of centrifugal pumps.
Why are centrifugal pumps used so much? Because they're versatile, simple in construction, and relatively inexpensive to buy. They're also easier and less expensive to operate, maintain, and repair. But just what is a centrifugal pump? Let's start by looking at its primary components.
When we break it down, we see that a centrifugal pump is actually quite simple, with only 6 main parts. These are the casing, the impeller, the shaft, the coupling, the bearings, and the seals, or packing. Let's look first at the casing. It's the biggest and most obvious part. Its main job is to house and protect the pump parts inside. It can be made from cast iron, steel, bronze, or even special materials, if that's what the job calls for. This is the impeller. It's the part of the centrifugal pump that imparts energy to whatever fluid's being pumped. The impeller is tightly attached to the shaft and rotates at the shaft speed. Impellers can be made from different materials, most commonly cast iron. When corrosive fluids are being pumped, impellers are most often made of stainless steel, plastic, or some special material. This is the shaft. It's connected to a driver, which might be an electric motor, an engine, or a steam turbine. The shaft turns the impeller. Steel is the most common material for shafts. Let's stop. Here's the driver. There's the pump itself. What links them? This, the coupling. It connects or couples the driver to the pump. And it does so for a purpose, to transmit power from the drive shaft to the pump shaft. Although they might seem simple, couplings are as critical as all the other components. They've got to be strong enough to withstand sudden changes in the pump's load and also those times when the driver might stop. Now to bearings. They support the shaft and reduce friction as it rotates in the casing. They do even more. They control the forward and backward movement, the thrust of the shaft, as well as the shaft side-to-side or radial movement. That keeps the shaft from rubbing against the pump casing. Bearings can be here, in the pump casing on small process pumps, or separated in special housings on larger ones. Last, are seals or packing. They're used to stop or cut fluid leakage around the shaft.
That's how a centrifugal pump's built. Now let's see how it works. Centrifugal force is the key. It's that force that tends to move an object away from the center of rotation. Sound too theoretical? A common example will show that you already understand the principle.
The example, children riding a merry-go-round. They spin, and children move outward. And as they do, they're subjected to a lot stronger outward force that tends to force them off the ride. That outward movement is called centrifugal. How does this relate to centrifugal pumps? In this way. When a centrifugal pump is working, the impeller rotates. Its blades stir the fluid, making that fluid rotate with the impeller itself. It's like a mini hurricane. The circular motion generates enough force to move the fluid away from the center of the impeller to the tips of the impeller blades. The movement of the fluid to the outside edge of the impeller creates a suction at the eye of the impeller that draws more fluid into the pump. If we look at the movement of an impeller, we note that the outside edge of the impeller travels faster than the inside center. So, to stay up with the impeller, the fluid has to move faster as it moves outward. That increases the energy of the fluid. The fluid leaves the outside edge of the impeller. As it does, what happens? It enters a specially designed area of the casing known as the volute. The volute is wider at the discharge nozzle than where the fluid leaves the impeller. There's more space, which causes the fluid to slow down. Its velocity decreases. The fluid gives up some of its energy. But that's not all. Energy just doesn't disappear. It's converted into pressure. And that pressure forces the fluid out of the discharge nozzle. The fluid leaves the pump at a higher pressure than when it enters.
So what does all this mean? Centrifugal pumps move fluids by increasing fluid pressure through centrifugal force. This concludes section 1. Stop the tape now and refer to your student manual. There you'll find additional information and a review. View this section of tape again if you'd like. And when you feel you're ready, just start the tape again and we'll go on to section 2.